Microwave antennas, slot antennas, a series on antennas and wave propagation, lecture number 5.19. Slot antennas belong to the category of microwave antennas. These antennas are widely used in the design of microwave communication systems like radars and instrumentation landing systems. Literal meaning of slot is an aperture, a opening. Slot antenna is basically a opening, an aperture in a conducting metal sheet. These openings or apertures in metal sheets are capable of radiation when properly excited. This led to the development of slot antennas. In the present session, slot antennas are introduced along with their feeding techniques. There exists complementary relation between slot antennas and patch dipoles. This complementary relation, is used to have the slot antenna analysis simplified, done with least difficulty. Here, one principle, Babinet's principle, is useful. Along with the Babinet's principle, Booker's extension, and related concepts like conjugate sources, complementary screens, all are introduced, described, and explained in the present session. Let us begin the session with a few points on its invention and basic features. Slot antenna was invented in 1938 by Alan Blumlein in order to produce a practical type of antenna for VHF television broadcasting. His intention was to develop a television broadcasting antenna. After good amount of effort, he came out with a slot antenna. Slot antennas are apertures or holes cut in a metallic surface, metallic sheet. A slot is usually with a length equal to lambda by 2 or more in a flat metal sheet. Metal means conductor. At frequencies about 0.3 GHz, these antennas cut in the skin of an aircraft or wall of a waveguide act as very convenient radiators. 0.3 GHz means microwave region. These are useful in many applications, especially where low profile or flush mountings are required. For example, on high-speed aircraft, low profile nature, flush mounting advantage facility. These are very much required for antennas that are there on high-speed aircraft. Imagine a high-profile antenna like a parabolic reflector over the surface of a high-speed aircraft. How difficult it is to maintain this parabolic antenna on the surface of aircraft while it is moving with high speed when the antenna is facing heavy wind pressure. It is almost impossible. So low profile antennas are only can work there. Slot antennas, of course, patch antennas, microstrip antennas. These antennas are low profile antennas and hence they fit, they suit, they only suit because of their low profile nature for mounting on high speed aircraft. In this slide is shown physical structure of a slot antenna in A and an array in B. Here is a metal sheet, flat sheet. A slot is there, rectangular in shape. Its length is lambda by 2. This fellow is fed by a line, transmission line. Now it transmits, radiates normal to the sheet. So in two directions it radiates into the slide and also out of the slide. In B is shown an array. Several slots are there. Notice these slots are cut in a narrow wall of a waveguide. Wave is fed at one end of the waveguide. It comes out from the other end. While traveling through the waveguide, a part of the wave is radiated out of the slots. So these slots are waveguide fed. The radiation from the array is normal to the length. Notice the distance between the slots. Lambda g by 2 here, lambda g by 2 here, lambda g by 2 here. We go a little bit deep into the dimensions later. For the time being, point to be understood here is that in B, radiation is broadside but in one direction, whereas in A, radiation is broadside but it is in two directions. Now we move to discuss some important features of slot antennas. Slot antennas are very efficient radiators when compared to their complementary counterparts, wire or strip antennas. Complementary counterparts. Complementary. Why slots are complementary to strip antennas? Reason is presence of conductor is characteristic of strip antennas, is the structure of strip antennas, whereas absence of conductor is structure of slot. So it is presence or absence. When we add a strip antenna to its corresponding slot, then it gives a total sheet, complete sheet. A complete conductor sheet comes into being. For this reason, as one completes the other, these two are said to be complementary to each other. Academic definition of complementary nature is given in the coming slides. For the time being, just keep in mind that strip antennas and slot antennas, they are complementary. These antennas are fed by a generator or a transmission line connected across it, or by guided wave incident on the slot in case of waveguide. These two are shown in the previous slide. When energized with a coaxial cable, the outer conductor of the cable is bonded to the metal sheet. To match the impedance of the cable to slot, cable is connected at the off center to the slot. A flat sheet with a lambda by 2 slot radiates equally well on both sides of the sheet. This point has already been made clear in the previous slide. A few points on radiation characteristics. The radiation is normal to the sheet. When the slot is horizontal, polarization is vertical, and when the slot is vertical, polarization is horizontal. Radiation from only one side can be obtained using a boxed large sheet or by feeding a slot with a waveguide. Feeding slot with a waveguide, giving radiation in one direction. We have already seen in a previous slide. A number of inclined slots can also be cut in the side wall of the rectangular waveguide, forming an array to give a directional radiation pattern. This aspect we have noticed in an illustration that is given in a previous slide. If the spacings of slots is lambda g by 2, their energization is in phase and produce a pattern with the maximum radiation broadside to the guide. From this, one can understand why the spacing is made lambda g by 2 between slots cut on the side walls of the waveguide. When the guide is lying horizontal, the radiated field is horizontally polarized. Here is shown slot feeding techniques. In A is shown coaxial line feed. B is also coaxial line feed, but in B, coaxial line connection to the slot is off center. So first one is center feed, second one is offset feed. Both belong to the category of coaxial feed. Here, both the slots radiate in two directions, into the slide, out of the slide. We can call it a bidirectional pattern. Whereas in the diagram shown below, A is waveguide fed slot. This is waveguide. Input is given here. Wave travels. Notice the waveguide is terminated over the slot cut on the surface of a sheet, conductor sheet. So radiation comes out like this. So here radiation is unidirectional. In B is shown boxed in a slot. Here is a box. This is a box. One side of the box is terminated over the slot. The box is fed by coaxial line. Here also radiation is like this, out of the aperture, out of the slot cut on the surface of the conducting sheet. A few points regarding radiation pattern. In case of vertical lambda by 2 slot, the radiation is horizontally polarized everywhere. The electric field has only phi component given by a formula. This formula is E phi of theta is cos pi by 2 cos theta by sin theta. Notice the similarity of this expression with the radiation pattern of half wave dipole. The similarity is a result of connecting relation, complementary connecting relation that exists between lambda by 2 slot and lambda by 2 dipole. If the sheet is perfectly conducting and infinite in extent, then E phi of phi is constant. So in azimuthal direction, field remains invariant with the direction. If the sheet is finite in extent, then there is a very little change in E phi of theta, but there exists drastic changes in E phi of phi. Is when the sheet is large. When sheet is finite, then there exists drastic changes in E phi of phi. E phi of phi is constant when sheet is large. One such change because of finiteness of the sheet is there comes nulls into being in all directions in the plane of the sheet. Another change is the pattern exhibits a scalloped or undulating characteristic. As the sheet length L is increased, the pattern undulations become more numerous, but magnitude of the undulations decreases, so that for very large sheet, the pattern conforms closely to a circular shape. This is descriptive information pertaining to radiation pattern from a vertical lambda by 2 slot radiator. Now, Babinet's principle. What is this principle? Why we have to study this particular principle? The analysis of slot antennas is quite a difficult process as it is, but this process can be simplified. This process can be made less laborious when we notice the connecting relation between slots and patch dipoles. They have complementary nature of connection. Because of this relation, the results that were already obtained by analyzing patch dipoles can be imported into slot antenna analysis, and then they can be used to find performance indicators of slot antennas like impedances, patterns, etc. after doing necessary modifications. This import from patch antennas into slot antennas is made possible by one principle known as Babinet's principle, along with its extension by Booker. Now, we spend some time on understanding Babinet's principle and its extension by Booker. In optics, Babinet's principle relates to transmission through apertures or hole in thin, perfectly absorbing complementary screens. So Babinet's principle is basically, it is part of optics. It is about the transmission of light through holes, apertures. According to this principle, the fields with a screen and a complementary screen, they are connected with the fields in the absence of any screen. Formally, it can be stated as the field at any point behind a plane having a screen, if added to the field at the same point when the complementary screen is substituted, is equal to the field when no screen is present. This is Babinet's principle. This formulation is actually meant for light. To use this principle, some amendments are required to be made, not corrections, in microwave engineering. Those amendments are made by Booker. Okay, to go further, to illustrate the principle mathematically, let us suppose there is a source at one end and two imaginary planes, plane of screens A in the middle and plane of observation B at the other end. Now we consider three situations named 1 to 3. Case 1. Perfectly absorbing screen is present in plane A, and in plane B there exists only a region of shadow. Let the field Fs behind the screen be F1 XYZ, that is Fs equal to F1 XYZ. XYZ means it varies from point to point. Case 2. The absorbing screen of case 1 is replaced by its complementary screen. Let the field, let us denote it by FCS. CS stands for complementary screen. B F2 XYZ. That is FCS is F2 of XYZ. Case 3. In this case, let no screen is present over plane A and suppose field F0 be F3. That is F naught is F3 XYZ. Then according to Babinet's principle, at some arbitrary point x1, y1, z1 on the observation plane, the fields in the three cases can be related through F naught is Fs plus Fcs. So the field in the absence of any screen is sum of fields due to a screen and its complementary screen. That is Babinet's principle. Now Booker's extension of Babinet's principle. As I already mentioned, Babinet's principle, it was formulated for light propagation, light transmission. Certain changes are required, certain additions or amendments are required in this principle so that it becomes applicable, it becomes useful in microwave engineering. These amendments were made by Booker. They are called Booker's extension. A few points regarding Booker's extension. In electromagnetics at RF means radio frequency. Notice radio frequency means, radio means wireless. Radio frequency means frequencies that are used for wireless communications. In electromagnetics at RF, thin perfectly absorbing screens are not available. Instead, what we have is conducting screens and vector fields, for which polarization plays an important role. Babinet principle of optics has been extended and generalized by Booker to take into account the conducting screens and polarized fields, that is vector nature of EM field. In this extension, it is assumed that the screen is plane, perfectly conducting, infinitesimally thin, and its complementary screen is having infinite permeability. It can be stated as follows. Let a source S1 to the left of an infinite screen S1 produce a field Fs on the right of this screen, and let a conjugate source S2 to the left of the complementary screen S2 produce a field FCS on the right of this screen. If the field in the absence of any screen is F0, then according to Booker's extension, F0 is Fs plus FCS. Basic formula is same. Field in the absence of any screen is sum of fields due to presence of screen and presence of complementary screen. But speciality here is it is extended to conducting screens and vector fields. In this extension, a conjugate source is used. What is conjugate source? It is one for which the distribution of electric and magnetic source currents are replaced by corresponding distribution of magnetic and electric currents. Electric magnetic source currents are replaced by magnetic and electric currents. This replacement interchanges E and H. For the incident fields, in this generalization of Babinet's principle, the conjugate sources are required for use with the complementary screens. When the incident field is essentially plane wave from a distant source, this requirement is met by simply turning the plane of polarization through 90 degrees, thereby interchanging the E and H fields. So in this slide, good amount of information, the useful information is given regarding conjugate source development. In this slide is illustrated Babinet's principle. Left side it is Babinet's principle, right side it is Booker's extension. Three cases, case 1, case 2, case 3. Right side also three cases, case 1, case 2, case 3. Here is a screen in A, complementary screen in 2, case 1, case 2, case 3, no screen. Booker's extension is associated with conjugate sources. In Babinet's principle, it is always the same source, but here it is conjugate sources. Case 1, a source is there, a slot is there in a sheet. In case 2, complementary screen is there, strip. In 1 it is a slot, in 2 it is strip, complementary. In Babinet's principle also, case 2 is complementary screen. Here also it is complementary. But the source, notice, this source is not the same as earlier one. Earlier one is horizontal. In case 2 it is, case 2 first one, it is vertical. In the second one of case 2 it is horizontal. Screen is of course a strip, it is also horizontal, complementary screen. In the first one of case 2, electric vector is vertical. In the second one, electric vector is horizontal. Case 3, here source is original source. Field is E0. This E0 is sum of E1 and E2. A few points regarding complementary screens. The slots and dipoles are quite related, and the analysis of slot radiators becomes less complicated when their relation with the dipoles is taken advantage. The results of dipole analysis can then be extended after modification to find behavior of slots without actually undertaking their analysis from scratch. The concept of complementary nature between slots and dipoles has become a key beneficial factor in the analysis of slots, and here the concept of complementary nature is explained briefly. Here is shown two sets of diagrams. In A is shown a sheet, conducting sheet. A small area is cut to make a slot. Notice the slot is of arbitrary shape. In B is shown a patch. It is a conductor. When the shapes of patch and slot are same, then slot and patch shown in A and B, they are said to be complementary to each other. Similarly, right side we have shown two diagrams. In A is shown a slot, in B is shown a patch. Slot is rectangular, flat is also rectangular. So shapes are same. When sizes are also same, then slot antenna in A is said to be complementary to dipole appearing in B. So for complementary nature, two things are important. One is shape, another is size. Both are important. Size wise, shape wise, they must be same. In general, out of two, one is said to be complementary to the other. When added together, they make a complete thing. When the things are screens, then the resultant ones are complementary screens, which are now formally defined. Consider an infinite plane conducting screen S1 having one or more apertures of arbitrary shape and size, and another screen S2 obtained from S1 by interchanging the region of metal and aperture space. Then the screens S1 and S2 are said to be complementary because added together they result in a complete infinite metal screen. A practical and useful example for complementary screens are one containing a slot and the other simply a flat dipole antenna. These are shown in the previous slide. Now we move into slot antenna analysis. The complementary slot dipole problem can be solved by considering them as a separate boundary value problems. For the free space regions about the antennas, solve wave equation in E. Del square E equal to mu epsilon dou square E by dou T square. And wave equation in H, del square H equal to mu epsilon dou square H by dou T square. using boundary conditions in the yz plane outside the perimeter. Ey equal to 0 equal to ez, hy equal to 0 equal to hz. Inside perimeter, hx equal to 0, ex equal to 0, and they can be used with del cross E equal to minus mu dou h by dou t, del cross h equal to epsilon dou E by dou t. The first one is Faraday's law, second one is Ampere's law to find other field. So notice these are wave equations and these are curl equations, Maxwell's curl equations. These equations require boundary conditions for their solution. Boundary conditions are given here. Using these boundary conditions, one can find E and H. Of course, it may not be so simple, so easy, but at least it can be done when the structure exhibits a certain regular shape, certain symmetry, without much difficulty. It is apparent that mathematically these two problems are identical. Thus, except for a constant, solution obtained for the slot in E will be same as the solution for H for the dipole. ES means electric field due to slot K1HD. HS means magnetic field due to slot K2ED. H magnetic field, D means dipole. E electric field, D means dipole. It follows E field distribution for the slot is the same as H field distribution of dipole and vice versa. In the analysis, we encounter a little bit difficult differential equations. Not only differential equations, we also encounter integration, complicated integration, line integration, especially is there in the analysis of dipoles. So, here are shown certain curves. These curves are around the structures of slot and flat strip dipole. Here is shown P, Q, R, S. One loop is shown. Similarly, J, K, L, M. These loops or these curves are used in the analysis while performing integration. Also, the impedance of the slot is proportional to admittance of the dipole and vice versa. The impedance of the dipole is, this is impedance of the dipole. This is impedance of the slot. Impedance of the dipole is V by I. V is integration over the curve JKL ED dot ds. This is a line integration. It would be more appropriate if we use dl instead of ds. So let us change it dl, because ds is used for surface integration. Now, ZD is V by I. V can be computed with ED dot dl. I is HD dot dl multiplied by 2 integration. Similarly, ZS can be computed. ZS is impedance of the slot. ZS plus ZD can be found equal to minus K1 by 4K2. While computing this particular relation, while arriving at this relation, we used in these integrals ES equal to eta HS, ED equal to minus eta HD. Now ultimately what we have is minus K1 by K2 is eta square, leads to ZS ZD is eta square by 4. Therefore ZS means impedance of the slot is eta square by 4 ZD. Notice here eta is intrinsic impedance of the space surrounding the slot. If it is a free space, eta becomes equal to 120 pi square. Sorry, 120 pi. From this ZD, using ZD, one can determine ZS as 418 at an angle of 30.5 degrees ohms. For a practical dipole, ZD is 65 ohms. For a practical slot, therefore, impedance becomes 550 ohms. See, this is the connecting relation. If you use ZD equal to 73 plus J43 ohms, then we will be getting 418 at an angle of minus 30.5 degrees. If you use 65, we will be getting 550 ohms. It can be extended even to a folded half wave slot to find its impedance. For folded half wave dipole, impedance is 4 into 65. And thus for folded half wave slot, it becomes 550 by 4 ohms. Here folded slot dipoles are shown. This is a folded slot, this is a folded dipole. Folded dipole is an ordinary dipole with one or more arms added. The purpose of the addition is to increase its input impedance, to have a better radiation resistance. So one can have a folded slot too, like a folded dipole. These are complementary. Their complementary nature is illustrated here. A comparison between slot and dipole is given here. The field patterns of slot and its complementary dipole are same, but with E and H interchanged. The directivity of slot and its complementary dipole are same. Length of slot and its complementary dipole are same, whereas width of slot is double the diameter of the dipole. Bandwidth characteristics of a slot antenna are same as for the complementary dipole. Widening the slot increases the bandwidth. And of course, impedances are related through ZS ZD equal to eta square by 4. One point to be kept in mind is directivity of slot is same as its complementary dipole. Directivity is an important parameter, maybe the most important parameter for an antenna. Now we come to an end of this session. In the present session, we examined slot antennas, their feeding methods along with Babinet's principle and its extension by Hooker. At the end, we have undertaken even an outlined analysis of slot antennas. Hope this session is useful to you. We meet again in another session soon with a new topic.